Welcome to Mistakes and Trade-offs, optimizing the hot path when premature optimization becomes early optimization. My name is Tomasz Lelek and I am working at DataStax. For example, I am developing the Stargate.io project. I am published author of Software Mistakes and Trade-offs, Making Good Programming Decisions for Mining. Previously, I was working at Allegro Group. You can find me on GitHub, Twitter and LinkedIn. So there is an old computer science saying that premature optimization is the root of all evil. It has a solid background because it's accurate for a lot of use cases. Without any input data about expected traffic and SLA, it's hard to reason about your code and its required performance. Optimizing random paths in code in such a situation is like a shooting in the dark. So you will complicate your code without a sane reason. Let's start by finding and analyzing when premature optimization is evil. Often, when we are writing our application code, we don't have much input data regarding its expected traffic. In the ideal world, we would always have the information about the expected throughput and the maximum latency requirements. In reality, we often need to follow a more ad hoc approach. We are starting by writing software that is maintainable and easy to change. However, as we are writing the code, we don't have strict performance requirements. In such a case, optimizing the code upfront has too many unknowns. When optimizing the performance of some code path, we are often increasing its complexity. This additional complexity arises from the fact that we are changing the code to be performance optimized. Sometimes we need to write parts of it in a specific way. In those parts of the system, we are trading off its performance over complexity. It may be a code complexity, but also maintenance or system complexity of the components that we use. Without the input data about the traffic, it may turn out that the given code is not impacting the overall performance of our main workflow. Because of that, we introduce additional complexity without the benefit of increasing the performance. Another pitfall we may encounter is optimizing code based on false assumptions. Let's see how easy it is to make this mistake. So let's consider a simple scenario where we have a simple account entity for which we are building our processing pipeline. So this is an account class. Then this simple code is using the stream API and hides the quite many performance optimizations. So you can see this account method that does the processing and try to find an entity for which we are building this processing pipeline. It's important to note that the stream abstraction works lazily. It means that it will execute the filter operation that checks if the account ID matches the argument as long as there is no account found yet. Let's clarify the usage of find any and find first. They are often used in wrong context. The laziness is achieved by using find any. This method will stop processing when any element is found. If we use the find first method, it would have the same behavior as the sequential processing approach. If this processing is split into parts, then find any may perform better because we do not care about ordering of processing. However, using find first will mean that the processing must be done in order and it slows down the processing pipeline. The difference becomes more important when we are using parallel streams. We created this code as the first approach. It is important to note that we don't have any performance information. The list of accounts that we are processing could contain a couple of elements, but it can also contain millions of elements. Without this knowledge, it's hard to optimize the performance of this processing. For the low number of accounts, our code will be good enough. For millions of elements, we may consider splitting the work into different threads. The one solution will be to create those threads manually, split the work into batches and then submit it into multiple threads. We can also leverage existing mechanisms that hide the creation of threads and split the work, such as parallel streams. Let's assume that you are deciding to introduce performance optimization to our processing code. We notice that the processing works in one thread. It means that we cannot split work and execute it concurrently, leveraging all cores of our CPU. One of the possible optimizations that we can do is to use the work steal algorithm. You would need to split the work into n independent stages. All input accounts will have n elements in it. Firstly, we'll split it in half into two threads. At this point, two threads will be responsible for processing half of the n accounts. Secondly, our code should do another split because not all threads are utilized. The work will be split into 4 of n accounts. At this point, every thread will be able to start the actual processing. The split phase should split the accounts into as many parts as there are available threads or cores. The parallel stream method will split the work into n parts. It will use fork join pool thread with a number of threads equal to the number of cores minus 1. It looks simple, but it hides a lot of complexity. The most important change is that our code is multi-threaded now. It means that the processing should be stateless. We shouldn't modify any state from any processing method, for example, filter. Because we are using a thread pool, we should monitor its usage and utilization. Another hidden complexity that the work steal algorithm has is the phase of splitting the work. This phase takes additional time, adding performance overhead to our code. The splitting phase overhead can be higher than the gain that we get from making it parallel. Because we based our optimization work on false or no assumptions, we cannot reason how this code will perform on the production. To validate if our performance optimization was efficient or not, we should write a performance benchmark validating both methods. We assume that the processing would work for n accounts, where n is equal to 10,000. Regardless if the number is based on the empirical data or our assumption, we should at least write a performance benchmark to validate if our optimization is valid. The benchmarking code will generate n random accounts with IDs from 0 to 10,000. We can generate a random string using the UID class. The fork parameter states that all tests should be in the same JVM. We'll be using the Java Microbenchmark Harness (JMH) tool for benchmarking. Before the actual logic, we should run a warm-up that will allow JIT to optimize code paths. It is configured using the warm-up annotation. We'll execute 10 iterations of measurements. That is good enough. The more iterations, the more repeatable results. We are interested in the average time that the method takes. The results will be reported using millisecond time units. Let's take a look at the benchmark initialization logic. The baseline method will execute the first version of our accounts finder logic. The parallel method will execute the improved version, that is using parallel streams. So let's execute the benchmark logic and see the results. Please note that the exact number may differ on your machine, but the overall trend will be the same. When we execute the benchmark logic, we will notice the performance of both solutions is almost the same. One of the examples run output would be like this. The parallel processing may be even slightly slower because of the split overhead needed before the actual work. If you increase the number of accounts, you might start noticing that the parallel version is slightly faster. Overall, the difference between both solutions will be negligible. The parallel solution's performance results do not justify adding the additional complexity that arises from using a multi-threading solution. However, the code complexity doesn't increase whether you choose parallel stream or standard stream. The complexity is hidden in the internals of the parallel stream method. We assume that the code will be called for a specific number of elements. In such a context, the second version of our code does not perform better. The problem is that the numbers used to conduct the test were a guess. In a real-world system, it may turn out that the number of elements that we will be processing will be substantially different. It can be higher or lower. It means that we will have more empirical data that can be used to optimize the code, but this time based on real-world assumptions. In that case, we can get back to optimizing the code, but this time using correct numbers. If you know upfront that the accounts will grow over time, you need to adapt your benchmarking code. Once you hit the threshold, you will notice that the parallel stream will perform better than the standard stream. In such a case, it won't be a premature optimization anymore. We looked at one aspect of the input information needed for useful performance optimizations. In real-world systems, we have a lot of code paths. Even assuming that we know n for all input processing, it may be not feasible to optimize all of those paths. We should know how often the given code path will be executed to decide if this is worth optimizing. There are code paths that are executed very rarely, like initialization of code. However, we have code paths that are executed for every user request. We will be calling this code hot path. Optimizing code on this path is often worth doing, resulting in substantial performance improvement of the overall system. In the next part of this presentation, we will learn how to reason about this hot path in our code. In the previous part of this presentation, we saw an example of optimization based on false assumptions. One of the essential data characteristics that are very useful when optimizing your code is knowing the input number of elements, that is n. It may be the number of requests per second, number of files you need to read. As we all know, an algorithm's complexity can be calculated by knowing what an input number of elements is. We can pick the proper algorithm, but we can also estimate memory usage. Knowing n is vital, but not all code in our application has the same importance in real production systems. For example, let's consider a simple HTTP application that may have different endpoints executed more or less often. The first process request endpoint is exposing the main functionality of our application. It is executed for almost every client call and does this main work. Let's assume that this endpoint is executed by our 10,000 times per second. We also assume that the n for both endpoints is calculated based on empirical data or the SLA that our service will offer. So the data that we are using is based on assumptions backed up with actual data. On the other hand, we have a different method that does more heavy work. The modify schema manipulates the data structure in the underlying database that this HTTP application is using. It is called very rarely because changing the schema is not a common task that clients are executing. Once the schema is changed, it will stay in the same structure for a long time. Let's assume that we measure the P99 latency of both endpoints. That is, 99% of requests are faster than a specific number. After some time, we will get results concluding that P99 latency for process request is equal to 200 milliseconds. For the modified schema, P99 latency is 500 milliseconds. If we looked at those measurements without the context of the number of requests per second, we could conclude that we should start from optimizing the modify schema endpoint. When you add the context about number of requests, it is easy to calculate that optimizing the process request endpoint will give us a more overall resource and time savings. For example, if we will be able to reduce the P99 latency for process requests by only 20 milliseconds, that is 10%, we'll get the overall reduction of latency equal to 200,000 milliseconds, because we can multiply the previous and after improvement and subtract them. On the other hand, if we will optimize the modify schema endpoint twice to 250 milliseconds, we will get a substantially lower overall latency reduction that is equal to 2500 milliseconds. Again, subtraction. Based on those calculations, we can conclude that investing time in optimizing the endpoint that is called more often will result in 80 times more saving than optimizing the endpoint that takes more time to execute. The path that is executed for the majority of requests is called a hot path. Finding and optimizing it is a crucial aspect if you want to optimize the performance of every application. It turns out that in real-world systems, the pattern of unevenly distributed traffic between code paths in our application is happening very often. There were a lot of empirical studies that ended up as a Pareto principle that can simplify thinking about our systems. Let's take a look at this principle in the next slide. So there were studies of multiple systems, organization, work efficiency, and software systems that found very interesting characteristics for most of them. We'll analyze it in the context of software systems, obviously. It turns out that a smaller fraction of code delivers a substantial proportion of the value produced by our software. The proportions that were detected most often were 80 to 20%. It means that 80% of the value and work that our system is doing is delivered by only 20% of our code. It can be presented by this graph. If we had a linear behavior, it would mean that every code path in our code has the same importance. In such a scenario, adding a new component to our system would mean that the value delivered to our clients increased proportionally. In reality, every system has a core functionality responsible for core business and provides the most value. The rest of functionalities that are not crucial, such as validation, handling edge cases, and handling failures, do not produce much value. However, they require 80% of the time and effort to build the whole system. Of course, the actual proportion will differ depending on the business domain and system. It may be 30 to 70% or even 10 to 90. The actual number is not important. What's the most important lesson from this characteristic? We can conclude that optimizing the smaller parts of our codebase will impact most of our clients. For example, let's assume that our service needs to provide the SLA for handling 10,000 requests per second. The average latency is 50 milliseconds. If you want to examine such a system by the performance tool, it's essential to set the correct number of threads, concurrent users, to execute requests to a system under stress. If we pick one thread, we will be able to run at most 20 requests per second because we have 1 second deducted by the time that one thread needs to process, and we have 20. Such a performance tool setup won't allow us to examine the system SLA because we need to handle 10,000 requests per second. However, once we know that one thread can handle 20 requests per second, we can calculate the total number of threads that we need. We can divide the expected number of requests per second by the number of requests that one thread can handle. It will tell us that we need 500 threads to saturate the traffic. Once we have that number, we can configure our benchmark tool accordingly. If the stress test tool is not able to create that many threads on one node, we may of course divide the traffic into n stress test nodes, where each test node handles a portion of the traffic. For example, we may execute requests from 4 stress test nodes. In that case, each of those nodes will need to execute requests to 125 concurrent users. So 500 threads divided by 4 nodes. Please note that those calculations may be a bit different depending on the performance tool that you use. If your performance tool is using an event loop, non-blocking I/O, you may execute more requests from one thread. In such a case, Firstly, you need to measure the number of requests that one thread can handle and adapt the rest of the calculations to that number. Finally, you should create a bit more threads than calculated because the calculations are based on average latency. There might still be some outliers that will slow down the concurrent threads. To see how many outliers we have, we can look at the latency of higher percentiles like P90, P95 or P99. Due to that fact, we may multiply the number of threads needed for an average SLA by some factor, for example 1.5, to allocate some extra threads in the case of a temporal slowdown of a system under stress. The next step that we can do is measure critical code paths regarding the number of invocations and the time that it takes. By having those numbers, we can detect the hot path and calculate how significant performance gains we can get from optimizing a small part of our code. Thanks to the characteristics of most of the systems that follow the Pareto principle, by optimizing our hot path, we can impact and deliver improvements for the majority of our clients. We'll apply this framework for optimizing a system that has defined SLA. In the next part of presentation, we'll build and understand the system and its domain. We'll try to optimize the hot path. Let's say that we have a WordService that has two functionalities exposed under two APIs. The first functionality that it offers is getting the word of the day. It calculates the offset specific to current date and returns the word with the index equal to this offset. The second functionality is validating the word. The user is passing the word as a query parameter and scans the directory for its existence. It returns the information about its existence in the response body. The next couple of slides of this presentation will have a lot of code. We don't need to dig very deep into this code, just enough to understand this service's basic functionality. The WordService is a core component of our system based on WordService interface. The getOfTheDay method doesn't take any arguments. It just returns the correct word. The wordExists method takes the word that should be checked and returns if it exists or not. The first implementation of the WordService is not trying to do any premature optimization, as we don't have any numbers regarding SLA or traffic yet. The core functionality for getting word of the day is calculating the index for a given day. The logic is simple, as it uses year and day of the year plus a multiplying factor to have a better distribution of returned words. We are picking the multiplying factor to be equal to 100, but it can be any number. The logic for calculating the word of the day is leveraging the scanner class that allows us to scan the file lazily. As long as you want the next line, we need to call the method that retrieves it. Once we are done processing, there is no need to load more lines. The logic is quite simple. It iterates over the file as long as the line number index denoting the day's expected word is not found. As long as there are more lines, we are executing our logic. Finally, if the current processing index equals the index of the expected word, we can just return the word and finish the processing. Please note that at the end of the processing, we are handling one edge case. If the index for the given word of the day is too high, no word is returned for today. It may happen when the index for a given day is out of bounds of the underlying file. The second business functionality that our service is delivering is validation if the specific word exists. The logic for getting this information is similar to word of the day, but in case if the word doesn't exist, we need to iterate over the whole file. The wordExists method tries to find the word passed as an argument. If the file loaded from the file equals the word argument, we can return true. It means that this word does not exist. Finally, if the word was not found after iterating the whole file, we are returning false. The logic for wordExists is not optimized as we did not define the SLA. We don't have any performance test to find the performance of the current solution yet. Finally, we can expose our logic under an API endpoint. Both functionalities are exposed as HTTP endpoints. I will not show that code here, but it's pretty simple. For those who would like to take a look at it, I will link to a complete source code at one of the last slides of this presentation. Let's assume that our traffic estimates and SLA states that the WordOfTheDay endpoint will serve one request per second. On the other hand, the wordExists will be called more frequently, 20 requests per second. Straightforward calculations will show us that it even exceeds the value from the original Pareto principle. It means that the wordExists functionality serves 95% of the user's requests. Before we start optimizing this endpoint, we should create a performance test for both endpoints to give us latencies. By knowing both numbers of requests and latencies, we can calculate the overall benefits of optimizing one functionality or the another. We'll use the Gatling tool for performance testing. We want to model two performance test scenarios. The first one should target WordOfTheDay endpoint and execute one request per second. The simulations using Gatling are written using the Scala programming language. Every simulation needs to extend the simulation class. The scenario for getting WordOfTheDay is straightforward. We need to execute a get request for a given endpoint. Every request will be executed in the context of HTTP localhost 8080 words URL. If you want to deploy the Word application on a separate server, you need to change this URL. Our API endpoint accepts and produces JSON format. The benchmarking scenario executes the get HTTP request of the WordOfTheDay endpoint. We are expecting the result to be equal to 200 HTTP response code. Any other code will be treated as an error. The second scenario is similar, but the HTTP GET request needs to send the word to validate as an HTTP parameter. Because of that, we need to feed the scenario with words that we want to validate. Our example words.csv file contains the following words. Please note that we have the word bigger from the beginning of the dictionary. We also have the word presence that is in the middle of it. Finally, we have a zoo word that resides at the end of a dictionary. Besides that, we have two words that do not exist. They will trigger a full file scan. The words.csv file is used by the validate scenario and passed as the query parameter to the API endpoint. The feeder will fetch words from words.csv and execute them randomly. Finally, the scenario is executing a GET request with the word query parameter. Once we have defined scenarios, we should inject them to the execution engine and specify the expected traffic. The first scenario is executing one request per second. The validate scenario, responsible for 95% of the client's requests, is executing 20 requests per second. Let's analyze the performance results for both scenarios. The WordOfTheDay scenario performance seems good enough. All requests of the WordOfTheDay endpoint succeeded below 800 milliseconds. The P99 latency is equal to 361 milliseconds. Let's now take a look at the results for validate words endpoint. The endpoint executed the majority of requests. The majority of requests have latency higher than 1200 milliseconds. The 99th percentile is almost 5 seconds. By looking at both results, we can see that wordExists performance is problematic. Fixing it will impact 95% of our customers. There is no need to prematurely optimize the word of the day, as the performance is good enough. It impacts only 5% of our customers. But we can calculate that as well. So let's calculate the performance impacts of both endpoints using the formula from the beginning of this presentation. The word of the day P99 latency is 360 milliseconds, but we have only one request per second. On the other hand, the wordExists latency is almost 5 seconds, so 5000 milliseconds. We can multiply number of requests per latency and we will see the overall impact on the system. So this is 360 versus 100,000 milliseconds. We can calculate that the word of the day is responsible for less than 1% of our service requests handling work. Once we have those calculations, it is obvious that we should focus and where we should focus our optimization efforts. The word logic takes 99.7% of the total workload of our system. We calculated that by dividing both workloads. Once we know that the wordExists is problematic, we need to get information from our code's lower level. We need to understand what parts of the code path takes most of the processing time. We can get that information by measuring the code that is on the hot path. Let's see how to achieve it. Initially, the code for validating if the word exists was simple and had no optimization. We didn't know at this point that optimization may be necessary. Now we have an input number regarding the number of requests that our service will handle. The performance test showed that we have a problem with latencies on the endpoint that serves 95% of our users' requests. The Gatling tests were black box, meaning that we get the information on how the specific endpoint performs, but we don't have any internal information about the most time-consuming parts of the system. As you remember, the wordExists method consists of two main functionalities. The first one is loading the file containing the words to check. The second one, the scan phase, that tries to find if the actual word does exist. We can wrap both stages into separate timers to measure every invocation of those methods and give us more detailed information about their performance. We'll create two timers. The first timer will measure the time that the loading of the file takes. The second timer will measure scan time. How long does it take to find if the word is valid or not? The timer will be executed for every operation and will give percentiles, average and also number of invocations. You can measure your code at any granularity level that suits your needs. Measuring every code path may impact the processing logic's overall performance, so you should use it carefully. Once your logic is optimized, you might decide to remove some or all measurements. After the Gatling performance test finishes, we can visit the URL that exposes metrics. This endpoint will show us all metrics in our application. You should see the section dedicated to load file phase. It will have data for percentiles. We are most interested with P99 percentiles, so let's take a look at it. The results are reported in seconds, and we can see that 99 percentile of load file action is equal to 7 milliseconds. The load file operation is not causing the performance problems that we detected using the Gatling test. We also have the count showing the number of invocations of the specific code. Using that, you can compare different code paths and see when most of the time is spent. It may be handy if you don't have predefined information about expected traffic or SLA. If you have that information, you can use the metrics to validate your assumptions. In such a scenario, you can deploy the application to production with metrics and calculate with code paths which code paths were invoked most of the time. By having this information, you can detect the hot path and focus on improving its performance even without the strict SLA information. Let's take a look at the scanner timer. We can see that 99th percentile is almost 5 seconds. It seems that we found the underlying cause of our performance problems. The scan operation takes a long time to execute and it takes most of the request processing time. Once we detected the underlying cause, we can start optimizing the hot path that needs to be optimized. In the next slides, we'll optimize our application's hot path and validate if our improvement results in better performance. We might consider implementing JMS image tests, asserting our code's performance at the lower level and getting faster feedback after our changes. The faster feedback would be possible because we don't need to run the whole Gatling performance suite every time we experiment with the implementation. I will not demonstrate JMH tests in this presentation because it will be too long. If you are interested how this step can be done, please refer to the chapter 5 from my book. Once we know where the problem lies, we can start optimizing the wordExists code path. We need to reduce the time spent on the scan phase. Let's assume that the words file that we are using for checking a word's existence is static and does not change. This assumption is very important in the context of our logic. It means that once we check if the word exists, the value will not change in the future. Let's implement the solution based on the cache and measure its performance. We need to construct a cache that we call the existing wordExists method if the given word is not present. We are setting the default eviction time to 5 minutes. It can be adapted once we have more data about production traffic distribution. We are constructing the cache where the word is a key and the information about its existence is value. We are using Guava loading cache library. When the specific word was not accessed by the eviction time, so the time passed, it will be removed from the cache. We are ready to run the Gatling performance test again. Let's see the results from our performance test. We can see that the performance of our solution increased substantially. The latency 99th percentile is equal to 65 milliseconds. It is almost 80 times faster than the initial solution. Once you perform an optimization, you can recalculate the impact that the specific parts of the code take. Our 99 latency was reduced to 65 milliseconds now. We can use the second section's formula from the previous part of the presentation to calculate the performance impact of the word of the day and wordExists logic. The wordExists traffic is 20 requests per second with P99 equal to 65, and the word of the day has 1 request per second with P99 360 milliseconds. Finally, we can calculate the percentage of the traffic generated by both endpoints. We can do it by calculating the traffic for the word of the day. Our calculations show now that the word of the day traffic is generating 21% of the workload of our system. The wordExists is responsible for rest 79% of the workload. We reduced it from 99.7%. The wordExists is still responsible for the most of the workload. However, as we calculated before, it impacts 95% of users' requests. After our optimization, the word of the day that affects 5% of the users' requests take 21% of the processing resources. If we seek further optimizations, we should calculate the possible time saving using formulas from this presentation. Let's assume that we can further improve the performance of both endpoints by 10%. For the word of the day, it will give us 36 milliseconds of time saving because we have only one request per second. Improving the wordExists performance by further 10% will give us 130 milliseconds of time savings because we have 20 requests per second. However, it may turn out that optimizing the wordExists performance by further 10% is infeasible or hard to achieve. We can calculate that only optimizing the word of the day by 30% will give us more time savings than optimizing the wordExists by 10%. If optimizing the endpoint by 30% is more feasible than optimizing the wordExists by 10%, we may decide that we should focus on the non-hot path optimization. However, as you notice, optimizing the hot path gives more benefits with lower efforts. In real life, optimizing the specific code path by 10% is quite more realistic than 30%. So, if you like my presentation and the approach that I've presented, you may also look like my book about software mistakes, trade-offs and decisions around that. It's available on the Manning website. Here is the link. So that was it. Thank you. I'm also enclosing a link to code from this presentation, and the whole book is free, so you can check out and run those examples by yourself. Thanks.